I'm excited to welcome you to our next session, which is starting with our biosignatures panel. My name is Sarah Tuttle. I'm at the University of Washington in Seattle, and I will not torture our running metaphor too much, but just say the staff are here for your safety and not your comfort. Let me introduce the moderator for this panel. Vikki Meadows will be moderating. She is my colleague and a professor and an astrobiologist at the University of Washington. She's also PI of the Virtual Planetary Laboratory team, which had a birthday this year and turned 25. So it turns out, I know, it's very exciting. We've been working on this collectively for a long time. All right, thanks so much.
Hey, thank you. All right, can people hear me? Closer, okay, all right. I have to be, okay, here we go. How's that? That's better. All right, cool. Oh, okay, so hello everybody and welcome to our biosignatures panel. Our panel today is 4 card-carrying astrobiologists and a largely imperturbable technologist at the end. So we're going to have a discussion amongst that group. And so our scientists are going to be sharing their very favorite astrobiology science cases with you and how these cases might actually drive the design of HWO. And then after that, we'll be asking our technologists to share emerging technologies with us that might support or enable our astrobiology. So that's sort of the format. If there's time at the end, we will also throw to the audience. So if you have questions, hopefully you get a chance to ask them. So the central theme that will run through the science cases you hear are basically that HWO needs to be so much more than just an oxygen detector. I don't know how many elderly people there are in this room who remember the XNIPS and TOPS reports and how we were going to have matched filter bands to look after O2 and ozone. We've evolved past that now. So we now know that when we detect a biosignature, it's really just the beginning of our quest, our potential biosignature, because no biosignature is going to be unambiguous. We're really trying to detect life on a planet that's incredibly complicated and has lots of different components. The exception, of course, is if you detect a modulated radio signal that encodes pi, then do let us know, because that is really probably the only unambiguous biosignature you'll get. And in that case, we don't need planetary context, we don't even need a planet. But for the biosignatures themselves, we need to do 2 things. One is we need to be able to verify that we've got a real signal and we're not being fooled by the speckles or some other kind of instrumental artifact, that we've identified it correctly. And ultimately, we need to be able to interpret it in the context of the environment we find it in. So in the first case, trying to get a better detection, the obvious thing is maybe to go for more exposure time and get better signal to noise, but we could also look for multiple bands if we have sufficient wavelength range. And we can also look for things like photochemical byproducts of the molecule we think we have. If the photochemical byproducts are there, it makes the probability that the parent molecule is there that much higher. For the environmental context, we need to look at 2 things. One is are there processes in the environment that are able to create the biosignature gas or surface feature or whatever abiotically without life. These are our so-called false positives. They could come from, say, volcanism or photochemistry. And then the other thing we have to look at is, are we looking at a habitable planet? Does it make sense that life would produce this signature in this environment? So, that oxygen you've detected on that raging lava world is maybe something you might want to question, right? So without further ado then, I would like the panel to introduce themselves briefly, and then after that, I will start posing questions. So we'll start here with Amber.
Great. Hi, everyone. My name is Amber Young. I am a researcher at Goddard Space Flight Center. I do exoplanet characterization and biosignature detection, looking at biosignature decision tree strategies and approach for exoplanet characterization. And I'm also an avid retrieval modeler.
Hi, my name is Eddie Schwieterman. I'm an associate professor at UC Riverside. I study the chemistry, climate, and spectral signatures of primarily terrestrial planets with a particular but not exclusive focus on potential biosignatures and their false positives and negatives.
Yeah, I'm Wogan from NASA Ames, where I'm a postdoc, and I study the chemistry and climate of planetary atmospheres, and I try to use that understanding to interpret telescope observations of exoplanets with an emphasis on biosignatures and habitability.
Hi everyone, I'm Ty Robinson. I'm an associate professor at the University of Arizona in the Lunar and Planetary Laboratory and with the Arizona Astrobiology Center. My work is mainly about understanding how we're going to recognize signs of habitability from the kinds of worlds that HWO is going to look at.
Hi everybody, my name is Kevin Fogarty. I am a civil servant at the NASA Ames Research Center. My work mainly revolves around developing emerging technologies for high contrast imaging. I'm kind of a transplant to the technology realm. I actually spent a lot of my previous life doing work on cosmology and large-scale structure of galaxies.
Okay, great. So I'm now going to ask the panelists each to share a favorite HWO science case. Please explain what it is, how you're getting your biosignature or whatever out of this, why you think it's scientifically significant for us to do this thing, and maybe even say why it might be challenging. So Amber, if you'd like to kick us off.
Yeah, for sure. So Proterozoic Earth and that science case is near and dear to my heart. We heard it talked about throughout this meeting in terms of having HWO have the capability to be sensitive to not just Earth as we know it today and as it's lived today, but also as we knew it in the past. And Proterozoic Earth presents a unique opportunity to be able to explore and characterize less oxygenated planets. Because for Proterozoic Earth at much lower oxygen abundances, in the visible spectral features for oxygen, like the oxygen A band at 0.76 microns, may not be as detectable for those lower abundances. However, in the UV, ozone still has a very strong spectral absorption, and it's a photochemical byproduct of oxygen. So being able to be sensitive to whether or not a planet is oxygenated or not, the UV might be the only window to do so for those earlier periods of Earth's history. And it's really important because Proterozoic Earth represents a large fraction of Earth's history, almost half. And so if we want an observatory that can robustly observe and characterize Earth, we need to be thinking about Earth through time and incorporate, every era of Earth's history that kind of presents that inhabitants and those characteristics that we're looking for. And so I've done a lot of work on the oxygen and ozone detectability question for Proterozoic Earth, particularly in the UV, looking at the spectral coverage that we might need, bandpass placement, and these are important questions to be asking now because they inform, sort of UV cornography questions and the trade studies in terms of narrowing in on what the actual observational requirements might look like for ozone. I think another important aspect to this as well is looking at potential spectral false positives for ozone as well, because there are a lot of species that absorb in the UV, but in particular, SO2 has an absorption feature that directly overlaps with ozone. So looking at modulating different boundary conditions and surface fluxes for SO2 and looking at sort of the spectral distinguishability between those two species has also been, really important for being able to characterize ozone and its detectability throughout Earth's history. So that's why Proterozoic Earth is sort of, and that particular science case is near and dear to my heart and sort of focuses on the strengths that we can take advantage of and leverage in the UV in terms of its strong spectral features for ozone and the relatively modest signal to noise ratios that are necessary to be able to achieve those ozone constraints. Wow.
Awesome, thank you. All right, Eddie, what would you like to do with HWO?
Yeah, I want to kind of address some of the talk this morning about how we might be fooled by potential false positives for biosignatures, and by that I mean planetary processes that are producing, for example, oxygen and ozone in an abiotic way through, for example, the escape of hydrogen and the accumulation of oxygen after the overwhelming of oxygen sinks. And so one way to, the problem is we don't know how common these mechanisms are. And the possibility is we live in a world or a universe where they're rare, and in which case we could be pretty lucky, or they're common, in which case we need to be more circumspect about our biosignature interpretations for habitable planets. And so one way to figure out which universe we live in is to look for oxygen and ozone outside the habitable zone, for example, in the Venus zone. So for example, we could look for abiotic ozone at separations closer than the inner edge of the habitable zone. The IWA is less onerous, say if you have a 0.4 micron cutoff than if you have 2 micron cutoff, so you can see much closer to the star. And so we might be able to figure out whether these mechanisms are common or rare. Another way to look for these false positives is to look for oxygen partial pressures that are too large to be biologically produced. So Earth has maintained a maximum amount of oxygen that's a bit higher than exists now, in the age of giant dragonflies and spiders as big as your head. Maybe not the world you want to live in, but clearly an interesting planet. But such a planet would be identified by having collisionally induced absorption features from oxygen that are at separate wavelengths than the O2.76 micron band throughout the visible and near infrared. And so we could look for those and see what kind of universe we live in.
Yeah, so my favorite science case was covered quite a bit earlier this week. But yeah, I want HAB-worlds to be able to detect Archean Earth-like biospheres. So right, this is Earth between 2.5 and 4 billion years ago. There was no oxygen back then, and the main biosignature was the coexistence of methane and CO2. And right, methane biosignatures, they could be more common than oxygen biosignatures. On Earth, oxygenic photosynthesis, it originated late and is a very complicated metabolism, whereas with methane, it was maybe one of the very first metabolisms and is relatively simple. So these could be more common biosignatures. And yeah, to detect the Archean biosignature, we need HAB-worlds to observe into the near infrared with pretty high signal to noise. So maybe Josh showed, or if you look at a reflected light spectrum of the Archean Earth, there's lots of methane features in the visible and the near infrared, but there's really just one CO2 feature out about 1.5 microns. So we need access to that CO2 feature to provide context for any methane detection. But we also need access to the near infrared to exclude false positives for the Archean biosignature. So people have imagined possible lifeless planets where you could have strange volcanoes that make carbon dioxide and methane, mimicking an Archean biosphere. But work has shown that these volcanoes would also make a lot of carbon monoxide. And on an actual Archean with life, we expect low carbon monoxide because life likes to eat carbon monoxide. So with HAB-worlds, if we have access to the near infrared, we can put a constraint on carbon monoxide and rule out this false positive. But yeah, so in summary, I just think the Archean Earth is a really important biosignature for HAB-worlds to detect. And as Josh said, we need access to the near infrared out to maybe 1.7, 1.8 microns to do that.
So given my introduction, you probably won't be shocked to hear that the science case that I'm most interested in, especially for this panel, was the Detecting Oceans on Exoplanets science case. Jake Lustigiger this morning did such a great job presenting on that, and that was co-developed by Jake Lustigiger, Nick Cowan, and collaborators. And so for me, what makes it so motivating is that we're talking about biosignatures and we want to understand if we're going to be able to detect life on exoplanets. But I think we also want to know, given a habitable environment, how frequently does life arise? And to answer that question, you need to be able to understand if that world has presented a habitable environment in which life could have arisen or in which life did arise. So I think habitability goes hand in hand with the biosignatures question. And in fact, in Josh Christensen's presentation, some of the scenarios that you wanted to rule in or rule out for biosignatures involved wanting to know what was on the surface and needing to know the surface conditions and needing to know if it was a desiccated environment or an environment that had oceans on the surface. And so as Jake so nicely presented, this strongly boils down to the inner working angle of your high contrast imaging system. So a lot of the detecting oceans on exoplanets science case relies on being able to access the kinds of crescent phases at which the glint signature from oceans becomes strong, and also at which the polarization signature from oceans becomes strong. And so, as was shown in Jake's presentation, the work from Vaughan et al. In 2023 demonstrated that if you can get your inner working angle from about 3 lambda on D to 2 lambda on D, you're talking about a 3 times increase in the number of worlds that you could access at crescent phases to potentially probe for habitability. But I guess something that I wanted to add was kind of beyond all that, I'm generally interested in the ability of Habitable Worlds Observatory to just be a general characterization engine for exoplanets. And so I'm excited about its capability to study the unknown. I want to be surprised by what Habitable Worlds Observatory finds. And I think we maybe wouldn't have done our job if we don't spend most of our time confused by HWO observations.
Okay, so thank you to the scientists there. So I guess thank you to the astrobiologists. So for Kevin, building the first mission ever designed to search for signs of life on Earth-like planets around sun-like stars will require some of the most advanced technology ever flown in space. So, Kevin, are there any emerging technologies that might help to enable those ambitious science cases, and how would they help?
Yes. Yeah, there is a whole plethora of just fantastic emerging technologies that are coming to the fore now. They are at different levels of maturity, and actually, recently we just got the Roses call back, and it's very exciting to see how many of these were selected as selectable. So going forward, there is actually a path to get these things to TRLs 3 and then 5. I like to think about the, at least from the perspective of coronography, since I spend pretty much all of my time designing the coronagraph instrument. Well, not a coronagraph instrument. I tend to think of it being sort of like 2 lanes of emerging technology development. One is the more traditional approach, where we take the things that we have a pretty decent idea how to build or develop, so apodizing masks, mirrors, and ask the question, is there a more clever way we can arrange these optics? Is there a more clever way we can design these optics? And there are a number of people today, a number of really good posters and really good talks, which show that yes, indeed there are many clever ways that will allow us to increase yields, that will allow us to push down on the inner working angle, improve throughput, improve bandwidth. But then on top of these more traditional approaches, there are these fantastic emerging technologies. And the one that I'm most familiar with and work the most on is, broadly speaking, we can talk about photonic technology. And this has the potential to be a real game changer. I mean, we're just all, excited about the possible future where we are basically able to do linear algebra directly on the light we observe. And so if you kind of think about the problem of coronography as in its most abstract sense, I have an electric field. That electric field is a superposition of wavefronts from a star, from a planet which I care about, from a bunch of other things. And I want to decompose that superposition. Well, if I have basically something that lets me do computation on the light itself, that is by far the most efficient way to do that. And we are, making some pretty decent progress in that realm. Additionally, AI-powered post-processing techniques, we saw an interesting talk about that the other day. That has the potential to really improve things. Wavefront control, both wavefront control and coronagraph design could very much aid in giving us broader bandwidths. So, right now we are typically, designing towards 20%, but there's no fundamental physical reason why wavefront control can't go wider or why coronagraphs can't go wider. Is it easy? No, but it's doable.
Yeah, and you were talking the other day too about ways we could increase or optimize our IWA without actually increasing the size of the telescope. Do you want to mention some of that too?
Sure, absolutely. So, and this is again where kind of like both the sort of like more traditional and more kind of like quantum-inspired versions of technology development come into play. In either case, we are looking at new technologies that can then beat down on the inner working angle. So with the photonic coronagraph, potentially we are talking about inner working angles on the order of a lambda over d. And so, for the near infrared, where that becomes a very important parameter, there's a path forward there. Also, with more traditional approaches, so like more cleverly designed apodizing masks, we might not be able to get down to 1 lambda over d and maintain contrast stability, but we can definitely, start pushing that envelope closer and closer in that direction.
Great. Do any of the rest of the panelists want to ask Kevin a question?
Sure.
Yeah, go.
Yeah, so with JWST observations, there have been problems with like offsets between detectors. So like with G395H, there's 2 detectors, and you get a transmission spectrum of a planet, and there are these systematic offsets that really are bad for interpretation, and we can't figure out why there's an offset. And is that, kind of thing avoidable? Can we anticipate that? Can we? Because I don't think this kind of problem was anticipated ahead of time.
I mean, that's somewhat of a difficult question to answer, right? Because we are in the early days of just designing notionally these instruments. Like you look at the stop models right now, and they're basically like a lot of what will be instrumentation is kind of like cut and paste right now. In principle, we can design instruments to be like passively robust to problems we anticipate having. Not really sure how we deal with things we haven't yet anticipated.
Yeah, no, not notes.
Yeah.
Okay,
Yeah, I was going to ask about inner working angle, unsurprisingly. So Kevin, for the photonic detectors, you were saying 1 lambda on D. For the non-photonic detectors, you said that you would be really concerned about 1 lambda on D. I commonly see 3 lambda on D as a quoted number that's reasonable. Where between 3 lambda on D and 1 lambda on D for the non-photonic coronagraphs do you start to really beat up the sweat?
I have yet to see something push below like 2 lambda over D while also being tip-tilt robust. Things are kind of like around 2.5 lambda over D, but still like let you, maintain 10 to the 10 contrast with a star of finite stellar diameter or reasonable tip-tilt robust. There are things that are between TRL 1 and 3 that are percolating through the literature that are in test benches right now.
Great to hear.
Awesome. Okay, are there any questions from the audience for our panel members? Yes, there's one up there, down here too.
Thanks, Chris Stark, NASA Goddard. So I have a follow-up comment and question about inner working angles since we focused on that so much. So I just wanted to state that this concept of an inner working angle is really a mathematical description of the chronograph, and JWC has already demonstrated that we can work interior to whatever that number is. So it really depends upon the details of the chronograph's throughput as a function of working angle. So even if it says if we come up with a chronograph that's 3 lambda over D, it's entirely possible you could observe it too. Just
right, yeah, and like the chronograph that's been studied for EACs 1 and 2, the vortex, does not have a nice sort of step function throughput curve. So it has its inner working angle, but there's also meaningful throughput that's within the inner working angle.
Yeah, exactly. So those are really powerful types of chronographs. The question I have is, if we're pushing down to chronographs that are operating at like 1 lambda over D with these PIC technologies,
right?
At some point we lose the spatial. We're no longer sort of doing coronography because we no longer are spatially resolving the image, and it's not clear to me how we subtract exozodi or deal with other sources of contamination. Have you thought about those sorts of complications and how we can still deal with those and try to pull biosignatures out at such a small working angle?
Yeah, so I'm going to answer that question from the perspective of a hypothetical photonic coronagraph, where when we're talking about detecting a signal at around 1 lambda over D, effectively what you're doing is you are looking at power in modes. And so you're right. At that point, I am not really clearly stating, hey, I've detected a planet, it's at this position in its orbit, it's at this separation and angle from the star. But what I can do is say, I have my sorted output of electric field modes. I can get rid of the stellar modes and then look at the rest and do some sort of post-processing analysis. I imagine that sort of ambiguity that you're describing between, for example, multiple planets or between planets and exozodi, you may need to rely on like spectroscopic demultiplexing sort of thing.
Oh, right, it's my turn. There's a famous figure, it's figure 1.1 of the decadal, I'm looking at it right now, that Sean and Giada made. And it shows the concentrations of methane and carbon dioxide and oxygen changing over time on the Earth as the Earth evolves from Archean to Proterozoic to modern. And the period where carbon dioxide and methane change places, for instance, in their concentration, lasts a few hundred million years. And oxygen goes up very rapidly by geological standards over a couple of 100 million years. So what I'm wondering is with the static spectra we'll get of planets in reflected light, is it possible through some form of modeling to distinguish a case where the atmospheric concentrations are essentially stable over a long period, have been or will be, compared to a case where they're essentially evolving rapidly on geological timescales? In other words, can you tell the static atmosphere from the rapidly changing one that we know occurred on the Earth?
I think, Nick, you might have an idea.
Well, I mean, you know, these are just such different timescales, right? Like, right, Earth's atmosphere over, you know, thousands of years is relatively stable. Like maybe even, like the lifetime of even oxygen in our atmosphere today it's a long lifetime. There's actually a lot of oxygen in our atmosphere. So it, you know, even if you have long-term geologic change, there is quite a bit of, you know, over thousands and thousands of years, quite a bit of stability. Yes, a planet will change over billions of years, but these are like, you know, these are big long-term changes from slow hydrogen escape and slow oxidation of the surface. I guess I will say is that it is possible, so with our oxygen today, there's a big reservoir and it's very imperturbable, but if you have smaller oxygen concentrations or where you could you know, detect it by its ozone proxy, that smaller reservoir is going to be more sensitive to change, and there, you know, there could be changes over relatively shorter periods of time. And I think it's, you know, up to various people in this room to figure out whether those kinds of changes or even like a seasonal change in that scenario would be observable, or whether that would be too hard with Hab worlds.
Okay, so I'm sorry, in the interest of time, we're going to finish so we can let the other speakers in the session get in here. But thank you to all of the panelists, and thank you to the audience questions as well. So.
And as we're switching over, I just want to also make sure to thank Niki and Giada for organizing this panel that went so beautifully. And thank you, Vikki. All right. With that, I'd like to welcome Vivian Yu, who's joining us from Caltech IPAC, talking about reverberation mapping. I'll reset the timer.
Okay, thank you so much. You can all hear me okay? All right, thanks. First of all, I want to thank the organizers for putting together such a wonderful program. I'm learning a lot about exoplanets and habitability, and I'm super excited about UVIFU. But for now, we're going to pivot a little bit to talk about black holes, and I hope that in the next 10 minutes, and not too much more, I'll be telling you about why and how we would want to study intermediate mass black holes using this reverberation mapping technique with HWO. And I know that there haven't been too many black hole talks in the program thus far, so I want to just spend a moment motivating why we care about black holes. I know that this particular picture has been put up several times in this conference so far, and a lot of you look at it and ask the question, are we alone? And I'm so glad you're doing that, so I can ask a different question. And when I see this picture, the question I ask is, you know, how did we get here, right? And the big elephant in the room is it's really that galaxy that's captured my imagination, my attention. And so how, you know, to figure out how we really got here, we need to figure out and understand galaxy evolution, how they formed and evolved through cosmic times. And as you might have heard from some of the talks by Yuichi and other speakers yesterday, that, you know, black holes, the supermassive black holes in the center of these massive galaxies, play an important role in shaping the life of those galaxies through feedback processes, for instance. And so it seems natural to me then is to ask, you know, how these supermassive black holes actually seed and grow on their own. And it seems that it's a question highlighted in the Cato, so hopefully it is a legit question to ask. But also, I was having a conversation yesterday at the reception, and I was asked, why do we then care about intermediate mass black holes, these low mass little guys? And you know, for those who know me, I actually typically work on supermassive black holes myself. So I asked myself that question: why do we care about the little guys? It turns out, if we want to know where they form and came from, it is important to find these intermediate mass black holes. Otherwise, we can't really understand how these supermassive black holes form. And so it wasn't too difficult for me to put together this slide that motivates why it is scientifically important to understand intermediate mass black holes. They are the missing link between what I define as stellar mass black holes, things that are less than 100 solar masses per se, and supermassive black holes that are greater than 1 million solar masses. And because we have different theories for how supermassive black holes may have formed, they would either, you know, from seed black holes that they grow through accretion of material or mergers. We need to find out what those seeds are. They're actually predictions that folks have made about, you know, how our observed properties of intermediate mass black holes can inform us about these scenarios. And also, the mergers of these IMBHs will be the gravitational wave emitters that will be detected hopefully by LISA. So we really truly live in this multi-messenger era of astrophysics. Now, they've of course been a little bit difficult to study, and so and why is that? And so in the supermassive black hole case, they tend to be, you know, these gigantic monsters in the centers of galaxies, and it's easy to locate except for the galaxy mergers that I actually study. It's really hard to locate those sometimes. But we know that roughly they are sitting in the center of galaxies, and if we have high resolution, really nice high sensitivity IFUs, we can actually trace the motion of gas or stars around the black hole within the sphere of influence to deduce what the mass of that massive object is in the center of these sources. And we've done that with you know, high resolution IFU and interferometry data so far. But that's really actually a technique that's limited to very nearby systems where we can resolve within the black hole sphere of influence. For things that are a little further away, when we can't do that, a lot of folks then rely on, you know, single epoch mass determination methods, perhaps on trying to get a width of the emission line that tells you something about, you know, how fast the particle is going, and that relies on a radius luminosity relation that actually came from reverberation mapping that tells us how the luminosity of that AGN correlates to the size of the, let's just call it the AGN structure, the broadline region. And so, but these are actually relations that are anchored on local massive sources, okay? And you can imagine the level of uncertainties that we might get when we extrapolate to other populations. And so for lower mass counterparts of these black holes, you know, they often don't sit nicely in like centers of galaxies. They're, you know, in these low mass objects, and where it's really hard to distinguish that central light. And I'm not going to go into the detail of, you know, the sensitivity plots here, but basically in the current landscape, we don't have the observational facilities to really resolve the sphere of influence in lower mass black holes at the limits. And also, if we want to look at for broad lines to quickly measure black hole masses, sometimes these can also be mimicked by supernovae remnants lines that, you know, could really dilute your signal. And so, reverberation mapping is a way of trying to resolve not spatially but temporally, you know, the structure in a structure. And I'm realizing that the time actually goes down really quickly. So I would just say that in reverberation mapping technique allows us to look at the stochasticity of the variability that's coming from the AGN that bounces coming from the X-ray corona, bounces between to the other parts of the AGN. And so by measuring the light curves of these different coming from the different bands or emission lines, that we can actually try to deduce the size of these different subcomponents in a structure using either spectroscopy or imaging. And this is actually not that easy. We've only have a handful of bona fide cases for intermediate mass black holes so far, and GC 4395 being one of the more famous cases. And just want to quickly say that we, in the paper that was just accepted last week, we actually found one of the first reverberation mapping signal in the mid-infrared. And this is a case showing a mid-infrared radius luminosity. Oops, I guess you can't see this. But on the left-hand panel, you can see the mid-infrared radius luminosity relationship, and the lower mass end is really poorly constrained. It's a little bit less pessimistic in the optical and UV band, but it's not that much better. And so overall, we really need to constrain this low mass end of the relation. And so now comes to HWO, right? Why we really need this big observatory with large mirror and UV capability. So UV is crucial for a couple of reasons. It probes really the hot inner regions of those accretion disks in the picture that I drew earlier. And also it harbors these UV lines like carbon-4 and magnesium-2 that are crucial for the high redshift folks to understand and try to measure the black masses of black holes found at high redshift, because those are the only lines that they have accessible. So we really need good anchoring from the local sources. Lower mass AGN also have very rapid variability. So in this study we did in the optical bands, we were talking about on the order of minutes, right, of lags relative to G band. And so we really cannot have too long we need high cadence and high fidelity images. And also, the reason that you need a large mirror is that in these low mass sources, it's really going to be hard to distinguish, the different stellar-like mass to light ratio in these sources. And so if you have low resolution images, then the variability is not going to be as easily distinguished. You're going to have large error bars. And so we need high quality images for that good host decomposition to get the signal from the black hole. Okay, so I hope that this is why I'm advocating for why we need high precision spectral spectrophotometry with the full UV to optical spectral coverage, but for emission line reverberation mapping, but also high resolution multiband imaging to really isolate the AGN light from the host. And so if we have a large number of sources and at lower masses, we can hopefully start to build statistics that can help us answer the question of which formation scenarios the supermassive black holes have. So I'm going to not reiterate some of the key points that I just mentioned, but instead use and just kind of prep you for, we talked about synergies, right? There's a lot of synergistic science that we can do with a lot of these facilities that are available now or coming up very soon. And in the -1 minute that I'm going to have, I just want to advertise my poster where putting on my hat as the proposal lead for the Roman Space Telescope, that we all know the launch is coming in 15 months. The Cycle 1 call is just right around the corner. So if you want to know more about it, check out my posters upstairs or come talk to me. And I'll just end with my cheesy quote that HWO will explore not just habitable worlds where life may begin, but also the seeds of supermassive black holes that shape cosmic structure. So this is a story of origin. And on behalf of my HWO SIG co-chairs, I would invite you to join our mailing list, and I'll stop there. Thank you.
All right, do we have some questions about those shy black holes that we need to understand the universe? Great, we have one here.
So I'm curious, do you think that the sort of high contrast imaging at a very small inner working angle, like 100 milliarcsecond, could help in any way for the black hole or AGN science case?
Yeah, that's an interesting question. So I have talked to exoplanet-minded instrumentalists before, and we've talked about whether we can apply AGN science cases. Turns out this was somebody who was working on an instrument on Keck, and the magnitude that they need in the star was much brighter than even my brightest local AGN. So I was giving them NGC 1068, and it was like, that's not bright enough, and I don't know what to do at that point. So that said, I am encouraged because I think the similarity between what we want to see very close to the base of the AGN is similar to what exoplanet folks appear to want to do, right? You want to image things that are really close with a bright point source in the middle. And so I personally am also very interested in the case of like resolving duals and binary AGN. So if there's some way that we can have the technical capability that allows us to image sources that are a little less bright than the stars that you have, but also decently bright nuclei, I think we have some test cases that we can try that on.
Hi, Vivian. So what you're proposing is that to do fast images of your targets. It's like few seconds, 30 seconds, and repeated images of your targets. Is that what you're proposing?
The short answer is yes.
Yeah.
I think that's because the idea is that we need very high cadence images in order to map that variability. And because right now, if you don't have a large enough mirror with low mass objects, it's really hard to distinguish that light. I'm going to say, if I can have my wish list, I would like a simultaneous, multi-band imager like that we have on some of the LCO telescopes, where we can have simultaneous, like GRIZ or some bands. We can actually do that, take that at the same time, so we can improve the efficiency further.
Thank you.
Someone almost dead center, you guys can race. And just a reminder to introduce yourself before your question.
Hi, yeah, Kevin Fogarty here. It sounds like in order to do this with relatively high redshift cases where you need to have this rapid cadence, your ability to do reverberation mapping is sort of like a function of mirror size. Do you have a notion of kind of like the limit in how far out you can get, or what sort of limit in the cadence you can achieve as a function of the mirror diameter?
Let me clarify one point in the premise, which is that I'm sorry I didn't make that clear, but I'm proposing to do this in local sources, actually. So that's going to be a question on my premise. That said, even for higher redshift sources, actually, I think the sensitivity is not going to be the limiting point, because actually, as we go to higher redshift, we're going to have brighter quasars and whatnot to do this with. It's going to be coming down to, like, yeah, if we want to locate the low mass sources at higher redshift, then that's going to be the difficult part. But like I said, the beauty of reverberation mapping is that we really need to just resolve this temporally, and that adds to, that gives a lot of room to play with than just a spatial dimension.
All right, let's thank our speaker. And welcome Dr. Jess Doppel, joining us from Durham University.
Okay, can everyone hear me okay? Brilliant, okay, no, don't go back. All right, so hi everyone, I'm Dr. Jess Doppel. I'm a postdoc at Durham University and also a co-lead of the SCDD that is exploring the nature of dark matter through ultrafaint satellites of galaxies within the local volume. But because I'm the first dark matter talk today, I want to step back and sort of build a little bit more of the picture of why we care about dark matter and the sort of theoretical framework that we exist in. So our current prevailing cosmological model is that of lambda CDM. And what that means is that in an expanding universe, cold or slow-moving dark matter, which is also collisionless or non-interacting, collapses via gravity into objects called halos. And over time, these halos merge from very low-mass objects to very high-mass objects. And at the center of these halos reside the stuff that we can see: galaxies, dust, planets, us. And us, as the weirdness, as the luminous matter, is about 15% of the matter budget of the universe, so quite small. Now, lambda CDM, while it is an elegant and very successful model, does have its observational tensions. and these tensions tend to emerge at small scales. And I think that this simulation illustrates this quite well. So we see in each of these panels a Milky Way mass halo that is simulated with 3 different dark matter frameworks. So we see CDM over in the leftmost panel, and we can see lots and lots of these little dots. These are what we would call subhalos. When we allow dark matter to interact in a self-interacting dark matter scenario, we also see quite a few of these subhalos existing. But when we go to a warm dark matter scenario in which we allow our dark matter particle to be a bit lighter and a bit faster moving, much of that small-scale structure, those small-scale subhalos, entirely disappear. So let's quantify this a bit better. So when we turn to simulations of galaxy formation run under different dark matter assumptions, we can kind of get an idea of the types of galaxies that should reside within these dark matter halos, again, in these different dark matter scenarios. So when we look in the regime of sort of higher mass, normal dwarf galaxies, we can see that all of our different dark matter models, which are shown here with different colors and line styles, tend to predict roughly the same cumulative number of satellites as a function of stellar mass. So it's quite difficult to disentangle in these scales what our dark matter could be doing. Now, as we start probing into lower and lower mass scales, we start to see divergences, particularly between warm dark matter scenarios, like these yellow and green lines, and cold dark matter and CDM scenarios. Now, this is the regime of what we would call ultra-faint dwarfs, named so because they are, in fact, ultra-faint. So this is an example, this little smudge right here of an ultra-faint dwarf around the Milky Way. This is Sculptor. So to quantify this a bit more, ultra-faints are very low mass, ranging from about 10 to the 5 solar masses in stars, down to a tentative lower limit of about 16 solar masses, depending on how you feel about that result. These galaxies are extremely old and extremely metal poor, and are really only well studied with the exception of 2 such objects within the local group. So what can we get right now with the state-of-the-art surveys that exist for Milky Way-like systems? So there's a few of these that exist, such as ELVES, or the Saga survey, which we're showing a similar cumulative satellite mass function here. And we can see that in this sort of setup, we can really only probe to maybe 10 to the 7 solar mass satellite galaxies, maybe down to 10 to the 6.5 if we're feeling a bit lucky, which is really only beginning to push into that regime where we should expect to see differences in our dark matter models. So this is all to say that we do need complementary surveys of lower mass satellites to start to understand the nature of dark matter through this particular type of method. So using these current surveys, we can really only reach right now constraints on the warm dark matter particle mass of something like 2.6 keV, maybe 6 keV if we are working with extremely state-of-the-art systems. But what do we need to really make this breakthrough science progress? So this plot is showing what a sort of limited or a limiting stellar mass of a hypothetical survey could give you on the constraint of warm dark matter particle with a number of hosts. So each of these lines here would show a 3 sigma constraint at a different warm dark matter particle mass. And we've defined 13 keV as what we would need for breakthrough science. So can we do this? Is this possible at all? Well, it will be. With the Habitable Worlds Observatory, of course. We will have the capacity to observe extragalactic ultrafaints, as well as their individually resolved red giant branch stars. Now, because ultrafaints are so low mass and so old, we do want to make sure that they have sufficient numbers of RGB stars to be detected in sort of a survey scenario. So using the stellar population synthesis code ARTPOP, we have taken the mass, metallicities, and ages of observed ultrafaints around the Milky Way and used those parameters to generate 5,000 in this plot, simple stellar populations that we are considering UFD-like. So we can see that for the lowest mass, ultra faints, there's kind of a 50-50 chance of whether or not they're going to host one or a handful of RGB stars. But when we start getting out into the regime of maybe 10 to the 3.5 solar masses, we have something like a few tens of these stars. So we are able to sort of use that as our limiting stellar mass. Now, RGB stars are quite bright, especially in the visible. And if we sort of look at this plot over here with the brightest RGB stars in each stellar population, G-band apparent magnitude is a function of distance, we can sort of reasonably observe these things out to maybe 10 megaparsecs. And we do have quite a few Milky Way-like hosts within our 10 megaparsec volume where we can observe our RGB stars. So what does this mean for constraining warm dark matter? So if we have our limiting stellar mass here of about 10 to the 3.5 solar masses, we maybe only need 5 to 10 Milky Way mass hosts to figure out dark matter. Great, wonderful, we've done it, right? No. This is a very idealized scenario, of course, assuming that you can observe every satellite around every Milky Way mass host. So how realistic is this? How are we actually going to be able to get these constraints? So of course, it's very expensive to survey the entire virial volume around a galaxy where we could fully sample the satellite population. So instead, we propose sort of a target instead. We fully survey an annulus around a galaxy. So for example, maybe the edge of the stellar disk, or about 20 kpc, and a further radius, so in this case, 40 kpc. Get the deepest observation we can there, and then forward model the rest of the satellite population. So we have a sort of model HWO that we have built, and by that I mean we've assumed a sample setup where we have a 6-meter mirror, that our observations are effectively diffraction limited, and built a detector that is an imager area of about 43,200 arcseconds squared, with some other engineering specs down below. And in order to get this fully sampled annulus, we would need to have sort of a tiling strategy, which would decrease in number of tiles per distance. And when we get to the total exposure time per Milky Way mass target, we find, oddly enough, that for distances up to 10 megaparsecs, that these all sort of reside within about 10 days to do each annulus. So 10 days per host per band to get down to 10 to the 3.5 solar masses in our RGB detection plan. So this is still a little bit expensive, but that's okay. We can further optimize this survey, and I will say that this is still a step that is in progress. So what we can do is sort of build an MCMC framework that optimizes a fraction of dwarf galaxies that we wish to observe. So in this example, we've said 20 with a threshold mass of 10 to the 3.5 solar masses. And we can downweight these larger survey areas that are going to take more time to observe. We have sort of an arbitrary factor here somewhere of 10 to the negative 5. And the resulting area is actually not really that unlike what we found in the previous sort of arbitrary example. So we are still sort of sitting in that regime of 10 days per host per band to get these observations. So as I said, this is still in progress, and this is the preliminary. Don't look at it, it's just there to be pretty. But we do need to still consider a few things, like the impact of integrated light on our ability to detect ultra-faint dwarfs. We do still need a framework from going from RGB counts and integrated light to a reliable estimate of stellar mass. Further optimization, of course, of the survey area, as I just mentioned, and the secret fourth thing that I forgot to put on here, which is building a very reliable forward modeling framework, which, of course, still needs some research, as ultra-faint dwarfs are still a very new thing. So I think I am 30 minutes or 30 seconds over time, so I'm going to just leave my summary here, and I'm happy to take any questions.
Okay. Oh, we've got questions leaping out of the audience. There's Janice is down here.
That was a great talk. The kinds of observations that you are proposing will enable a tremendous amount of science for other galaxy research areas out to 10 megaparsecs. And so one can imagine not only creating, I mean, this as the basis for bringing in other people who study star formation and stellar populations and really make this a key project for HWO. Have you had those discussions yet?
Sort of, we'll say qualitatively with like my boss. But no, I would be happy to have some of those conversations because certainly I come at this from a very theory-oriented perspective. I have had a lot of thoughts on like, getting ideas about like the stellar populations and constraints that you can put on like formation time, which also would further, or formation time of ultrafaints, which would further sort of constrain that warm dark matter particle mass, or reionization. Like there's so much you can do with that. So yeah, absolutely, I would love to have those conversations.
That might be a good topic for the panel that we're going to have tomorrow, which will be on cosmic origins. So thank you.
Okay, other questions? We have, oh, yeah, great.
I may have missed it, but so what is unique about doing this with HWO versus like ELTs?
The resolved RGB stars. So if we had something like a spectrograph in addition to the photometry, which this case really does only focus on the photometry, you could get some very, very detailed stellar population information about those sorts of objects. I am a theorist, so I can't entirely answer this question. I would be lying to myself if I could, but I would be happy to have sort of a bigger discussion about that after.
What was the spatial resolution that you were?
So we were working with diffraction limited, so 0.02 arc seconds.
Hi, it's Paul McNamara from the European Space Agency. We actually have a study of a mission called Arrakis, which is doing very much this science. How is this complementary to something like Arrakis? Or Euclid is also doing very similar.
Yeah, so I'm only familiar with sort of the stellar stream projects going on with Arrakis, so I'm not entirely sure what the science case is with the ultrafaints.
It's basically doing the same, looking for the ultra-low surface brightness dwarfs around about roughly 100 nearby Milky Way galaxies.
Okay, yeah, so I guess this could be complementary in the sense of like getting better statistics with different instruments from different telescopes, building better photometric or spectroscopic information about those galaxies, the individual stars, and combining those catalogs would be very cool. I don't know if that answers your question.
And we have time for one more question. I think I saw someone up here. Is that true? Nope. All right, let's thank our speaker. Ideally, this would open. All right, let's welcome Bryce Wedig from WashU, which is always confusing from me from the University of Washington. Welcome. I will flip over the pen as soon as I sit down.
Excellent. Thank you. As mentioned, I'm Bryce Wedig. I'm a grad student at Washington University, working with Professor Tansu Dailan, and I will talk about dark matter substructure in galaxies, but a different probe from what we just heard. So we know that there's lots of dark matter in the universe. I can skim over this because the previous speaker did such a nice job setting this up. But unfortunately, we don't see dark matter directly here. We can observe it indirectly through its gravitational effect, which is the probe I will eventually be talking about. So through weak gravitational lensing and working backwards, we're able to map out the distribution of dark matter at cluster scales. But what happens when we zoom into the galaxy scale? Well, we've just heard that your luminous galaxy here lives in the center of a dark matter halo. But what I'm interested in, and what we don't yet understand well, is what happens at subgalactic scales. In particular, I'm interested in these subhalos, these smaller clumps of dark matter. How many are there in a typical galaxy, and what are their properties? Because these questions are tied directly to the microphysics of dark matter. Now, hopefully this looks familiar. So there are lots of theories of dark matter out there, and when we look at cold dark matter, we see lots of little subhalos. Cold dark matter's subhalo mass function, which again tells you how many subhalos are in each mass bin, follows this power law where you have a couple of large subhalos and many, many small ones. However, warm dark matter in the middle predicts a suppression in the subhalo mass function at lower mass scales. And this mass scale has to do with the particle mass. Then we also have self-interacting dark matter, which is often talked about in this science case. And while self-interacting dark matter can do some interesting things to the subhalo mass function, what we're often interested in is the density profile. So the self-interaction term leads to some interesting physics in the cores of these subhalos, which leads to flatter profiles. Now, here are some subhalo mass functions. First off, to distinguish from the previous talk, I should mention that the probe I'll be talking about, we're thinking about dark matter substructure much, much further away. We're talking redshifts out to 2. So in this particular case, I've just grabbed some massive system out at redshift 0.3. Now, when we look towards the right in this 10 to the 9, 10 to the 10 mass bin, for this particular system at this particular redshift, maybe there's 0 or 1 system. And with current instruments, with the probe I'm about to discuss, this is sort of the area that we are sensitive to. But as we go to the left, to the lower mass scale, things start to get interesting. We start to see deviations in the subhalo mass function, where cold dark matter might be predicting hundreds or even thousands of these low mass subhalos, other theories of dark matter predicting something different. And so this is a region with an instrument with a very large aperture and an ultra-stable PSF we might be sensitive to. And that's why we're so excited about HAP worlds. But of course, this begs the question, how are we actually going to detect these low mass subhalos at high redshifts? And we're going to do that with gravitational lensing, but a more dramatic kind. So we imagine something bright in the distant universe. Here it's a quasar. And as that light comes towards us, directly along the line of sight, there happens to be something massive, a galaxy. A lot of its mass is in dark matter. It has lots of subhalos. And it's going to distort the space-time around it so that as the light travels towards us, that light is bent inwards. It's also going to magnify and distort and create multiple images of that background object. Now, if a subhalo is in the right spot, it will leave an imprint, a perturbation on those lensed images. This is called strong gravitational lensing. And these objects are, I'll be referring to them as strong lenses. This is a strongly lensed quasar from HST. Often we're working with galaxy strong lenses. So here's a beautiful example from HST forming a nearly complete Einstein ring. Now, these objects are very rare. We require very close alignment of these objects to get this dramatic of an effect. And so today we know of about 1,000 of these systems. The candidate list is in 10, 20,000 range. Although this is being contributed to by Euclid and very soon by Roman. And so in the next 5 to 10 years, we expect to go from maybe a couple hundred systems that we've imaged with HST to have that high angular resolution photometry all the way to order 10 to the 5 from LSST, Euclid's wide survey, and what Roman will be able to do. So that means that by the 2040s, what we would hope for is a large population to choose from of strong lenses where we can take the most promising candidates for substructure characterization, so highest in our targets with complex source structure, to follow up with HAP worlds. Now, the two most important things for probing lower mass subhalos with strong lenses, in order of importance, first, SNR, obviously. But second is angular resolution. And that's because the deflection angles that you expect from subhalos are on the order of milliarc seconds or tens of milliarc seconds. So here I've simulated an LSST and HST image of the same strong lens system, and this is the simulated HAB-worlds image. So we can resolve all kinds of complex structure in the source galaxy and be sensitive to perturbations from low-mass subhalos. Now it looks like I'm picking on LSST here. I promise I'm not. LSST is going to do tremendous work for strong gravitational lensing, just not this particular science case. And so to forecast what HWO is going to be able to do for substructure detection with strong lenses, we took a software pipeline that we originally developed for Roman and then extended it to HWO. And the details of this pipeline are available in a paper that was published recently and was also covered in a press release from Space Telescope in June. We are also conducting a data challenge right now with some collaborators at Stony Brook using this pipeline. So if anyone is interested in hundreds of thousands of simulated Roman images of strong lensing, I would love to chat about that. What this pipeline allows us to do is to go from a realistic population of galaxies drawn across the sky and across cosmic time, all the way to realistic simulated exposures, and we can then take those and feed those into subhalo detection codes to evaluate things like survey and instrument design. And so here's a very preliminary look at subhalo detectability with HWO. So we start out by simulating a population of high SNR strong lenses, which are relatively nearby, just to get a sense of what we might have in the early 2040s. And then we draw realistic subhalos for them, accounting for things like redshift dependence and scatter in the mass concentration relation. That's what I'm showing on your left. And then we evaluate subhalo detectability while varying these EACs. So here again is a science case that is going to benefit greatly from a large aperture. And I suspect that as we improve the instrument model and as I incorporate things like a more realistic PSF and so on, and also as we shrink the target list to really isolate just the most promising systems, again, this requires fairly long exposures, that these lines will spread out even more. But what this means is that we expect HWO to be more sensitive to lower mass subhalos by at least an order of magnitude or more than we are today. So looking forward, a couple of the things that we'd like to do. First, I mentioned this more accurate instrument model. In particular, I'm very interested in a more realistic PSF with some of these EACs with the off-axis secondary mirror. This is a science case that's very sensitive to that sort of thing. But then we'd also like to take the next step to think about what kinds of constraints could we put on different dark matter models given some number of systems and some observation time. And I will leave you with my summary points and just mention finally that there is an SCDD on this particular science case if you would like to learn more. So thank you.
All right, we have time for some questions. Yep, there's one here.
Hey, Bryce, thank you. Great talk. Mark Postman here. I know you know the answer to this, but I'm asking you the question on behalf of Lee Feinberg. Because the ELTs will have, in the J-band or even H-band, have a similar angular resolution as HAB-worlds and Visible. So why can't you do this on the ELT?
Sure. So the ultra-stable PSF is a really important part of this. Yeah, so we're doing very long exposures here to be sensitive to that milli-arc-second scale lensing. We're really crossing our fingers for a large aperture space-based observatory.
Can you say how stable the PSF needs to be?
How stable?
photometric, you know, something.
I'm afraid I don't have that number off the top of my head. I'll have to follow up about that.
Okay, any other questions?
Hi, Eric Burns, LSU. When you talk about, constraining dark matter models, do you mean phenomenological? Do you mean ones, rooted in particle physics? In particular, can you also do with Hab worlds the capability to distinguish mixed models, so fractions of cold and fractions of warm?
Sure. So things, of course, get tricky with mixed dark matter. Typically, the way that this is done in the literature is you vary, say, one parameter. So I showed that subhalo mass function earlier. We're going to vary the ultralight dark matter mass. We're going to vary the half mode mass or the thermal relic mass of warm dark matter, see how many subhalos are predicted, what we actually observe, and then go from there to make those constraints. Again, mixed dark matter isn't something that has been explored just yet. Our detection sensitivity isn't to the point where we can really investigate that, but certainly in the next couple of decades we would hope so, and that's something that we'll be looking more into.
Okay, thank you.
Any more questions for Bryce? All right, let's thank him again. And let's see here. All right, and let's welcome our last speaker. Steve Finkelstein is here from UT Austin.
Thank you, Sarah. Great. All right, thanks, Sarah, and thanks, Janice, and all the organizers for running this wonderful meeting. So normally I would come here and talk to you about all the wonderful work that JWST has been doing in the early universe, and I could spend 3 or 4 hours doing that. I'm not going to do that. What I did try to think about are what are some of the questions that we're developing from JWST observations at early times that we won't be able to answer with JWST, and we need something like an HWO to answer. The talks can be primarily qualitative, not too quantitative. When I did need numbers, I assumed something like a 7-meter aperture, but following a discussion we had at coffee, I just thought I would say for galaxy evolution, 6 meters is pretty exciting. 8 meters is getting to be transformational, and 10 meters is groundbreaking. So ignoring some of the memes on Slack about talking about 10-meter telescopes, I think that would be great, but I will leave that to you all. So the key question that I tend to think about are when did the lights first turn on in the universe? The Big Bang, as we know, was 13.8 billion years ago. You don't get stars and galaxies immediately. Soon after the Big Bang, the universe is quite hot, it's quite dense. We need to wait for the expansion to let the gas to cool down and condense and collapse and form stars in dark matter halos. And exactly how long that process took, we don't actually know. And so we'll go through briefly, because Yuichi did this yesterday as well, this timeline of the universe, where you start way over on the left with the first picture we can take of the universe. This is the cosmic microwave background radiation. This comes from a time about 400,000 years after the Big Bang. Again, well before the era of stars and galaxies, but we can get a good idea of what the initial conditions were. We go all the way over to today, way over here on the right. I should say I have time on the top and redshift on the bottom, so you can pick which axis you're more comfortable with. We exist today over here at redshift 0, and when we look at the universe around us, as Vivian said, we have these big, beautiful, morphologically complex galaxies. We can classify them in the Hubble sequence. We would like to know how these galaxies formed and evolved. Thanks to a couple helpful features about the universe. The first one is that light travels at a certain speed. It doesn't move instantaneously from one place to another. That lets us look back in time. When we look at objects that are far away, we are literally seeing them as they were in the past. Also, due to the expansion of the universe, galaxies that are moving away from us, which is pretty much all of them, have a redshift imparted on their spectra. And that lets us place them at a distance, and distance is fine. I tend to think about it in terms of time. I want to place galaxies at different epochs. So let's move back in time to about a redshift of 2. This is about 10 billion years ago. And broadly speaking, when you look at galaxies at a redshift of 2, you can see the same type of spiral and elliptical galaxies that you see in the local universe. So if we want to see how those galaxies form and evolve, we need to push to yet earlier times or yet higher redshifts. We could push the wonderful 35-year-old Hubble Space Telescope to its limit. That's at about a redshift of 10. Hubble found Galaxy 1 at redshift of 10. Probably wasn't the only one. We were probably just seeing the tip of the iceberg, but it did show us that at that time, 500 million years after the Big Bang, the universe had formed stars and galaxies, and in fact had formed them on big enough scales that we could see them even with our smallish 2.4 meter space telescope. But what Hubble did not allow us to do is answer this question: when did galaxies form out of the cosmic dark ages? And so we had this sort of time window motivated by theory, somewhere between redshift 10 and 30, which is something like 100 to 400 million years after the Big Bang, that was completely unexplored before the era of JWST. Something that happens when these first galaxies form and evolve is that they start the process of reionization. Reionization is kind of a technical field, but you can think of it as the last major phase change of the universe when ultraviolet high-energy photons from those first stars and galaxies ionized all of the gas in between those stars and galaxies. And this is just one theoretical prediction for what that might look like. We know that stars and galaxies are clustered, so we expect reionization to be inhomogeneous. It's going to start in the densest regions and propagate outwards, and it will take some period of time before you can ionize all of that gas. We have a pretty good idea of when reionization ended, somewhere around redshift 5.5 or so. We don't know when it began. We don't know how it proceeded both temporally with time as well as spatially. And so these are big questions that are still unanswered even now after several years of JWST data. And the reason why I get really excited about reionization is it was both started by the smallest systems, and probably the energy budget was dominated by the smallest systems. And we never actually, even with a 10-meter HAB-worlds, we won't actually be able to resolve those systems. But we can infer their presence by studying the evolution of reionization. So we'll come back to this in a little bit. As you know, JWST was built to study this. Science case number 1 for JWST was first light in the universe, and it has absolutely delivered on that. So we're going to talk a little bit about JWST, but I do want to take a minute to say, why should we care? I know we're here to talk about, are we alone, life here on other worlds, but really understanding the formation of our own Milky Way galaxy is the ultimate origin story. Everything, our bodies, the planet around us, the stage I'm standing on, are made from elements that are formed in stars. The very first stars that we're trying to find in the early universe are the sites where the very first heavy elements, the very first life-promoting elements were created in time, ultimately culminating in life. Exactly how early, we don't know. So if we can identify when and where galaxy formation began, we'll be able to start the very first sentence of the first story of the chapter of the book that eventually led to human existence. So let's come back to JWST. So I'm showing here an image from our CIRRUS survey, one of the 13 early release science programs. And within days of some of the first data, including data from CIRRUS being released, astronomers learned 2 exciting surprises about the early universe. And the first one, you've probably heard of both of them. The first one is that there are a whole lot of bright galaxies at early times. Okay? Unexpectedly bright galaxies form very early in our universe. You may have heard that galaxies were too massive. We don't think that's the case. And we don't actually think these are too bright, but it is telling us that something interesting is happening. And just to give you a sense of what I mean by surprising, this is a plot of the sort of star formation rate density, the total amount of star formation in the universe as a function of redshift here. The blue sort of line is kind of what we expected, and the red symbols are what we observed. This is just from the CIRRUS survey, but this has been validated with larger data sets going on. So more star formation than expected at early times. And the second one, maybe even more exciting, is that the early universe contains abundant accreting supermassive black holes. We've identified these objects from their broadline regions. This is one of the first ones, also from the CIRRUS survey, from a paper by Dale Kasevsky, where we see, oh, I went ahead too fast. Back to little red dots in a second, where we see this, you can't see the laser, but there's a broad emission line of that component. And we infer that as being due to the broadline region around a supermassive black hole. And we can use scaling relations like the ones that Vivian talked about to infer the black hole mass. We've also discovered that there is a new population of galaxies known as little red dots. This is what they look like. This is what we actually think they might look like. This is an artist's rendition that's going to come out in a press release next week on the highest redshift confirmed little red dot at a redshift of 9.3. And I won't have too much time to talk about little red dots. Just wanted an excuse to show this beautiful picture. But we will talk about what HWO can do for black holes. So let's come back to surprise number 1, too many UV luminous galaxies. This is a suite of predictions for how many galaxies we should find per unit area as a function of redshifts. This is from, you could count the lines, I don't know, like a dozen different models, and we're plotting it basically all at redshift greater than 9. Where we didn't have observations. So the theorists didn't agree, but that's not surprising. There was no data to bound these observations. But when we did get data and we placed it on this chart, we can then begin to constrain these models. And the exciting thing is that the abundance of galaxies we found was basically at the high end or even higher than all of these predictions. The observations are this gray swath here. Okay, so these predictions didn't have this data to motivate it, but of course, we now have these observations. Theorists can come up with a lot of ways to try and tweak their models to match these observations. So there are lots of potential solutions. This is another version of that same plot. The red symbols are data, the colored lines are models, and now some of the models are going through the data. Okay? There are a lot of potential solutions. Many of them focus around more efficient star formation. Maybe gas clouds in the early universe are more efficient at making stars, and the reason why this might be is that at early times, the dark matter halos are more dense, the gas clouds in the galaxies are going to be more dense, and we think that if the gas clouds are more dense, a higher fraction of that gas turns into stars, and in particular, they come in the form of larger dense-bound star clusters. And so this is a more recent prediction from a paper by Rachel Somerville where she implemented this, she called it a density-bounded, density-dependent star formation efficiency in their model, and now their model in red does a pretty good job of matching my data in gray. So this is just one possibility. But of course, we want to say, what predictions could we take from this model that we can test? We can empirically test this model by trying to look at galaxies and see if we can see an increased fraction of star formation taking place in large, dense-bound star clusters. So we just want to take images of galaxies. And we can do this with JWST, but only for a precious few galaxies. We're really limited by spatial resolution. So this is an example from a paper by Seiji Fujimoto, who discovered a galaxy that was highly lensed, magnification of about a factor of 30, at a redshift of 6. And what I'm showing here on the bottom, on the left, you see an image of this galaxy with Hubble. It's a redshift 6, so you can see it. Looks like a regular galaxy, kind of unremarkable. With JWST, the image in the middle, and then zoomed in on the right, you can see it's actually broken up into 15 individual different large star clusters. Okay? So we can only do this with the resolution of JWST, but also combined with the magnification of lensing. Lensing is boosting the angular resolution by something like a factor of 5, letting us see these star-forming clumps with sizes of 10 to 20 milliarcseconds. Okay, and again, this is in a galaxy that if you didn't have that either resolution boost and lensing boost with Hubble, just looks like a regular old galaxy. So this, I think, is an exciting science case for HabWorlds, which is observing star clusters around cosmic time. So if we can push to bluer wavelengths and higher resolutions, we can study this process across a significant fraction of cosmic time, and in particular see if there is evolution that would help us see that the star formation efficiency may be changing at high redshift. So a typical high redshift galaxy has a spatial size of something like 0.2 to 0.3 arcseconds. If we want to make a wish list, I would say we'd like to break that up into 10 pieces. So maybe we want a spatial resolution of something like 20 or 30 milliarcseconds. And so this is a chart I made just for myself as I was making this slide, assuming a 7-meter aperture, just saying what is the diffraction limit as a function of wavelength. And so we can get down to these scales with HabWorlds in the red stream UV at a redshift of less than 5. At a higher redshift, you could pair this with AO imaging with something like the Giant Magellan Telescope and do this to higher redshifts as well. And so just to highlight what this might look like in this figure, this is that same galaxy on the last slide. I forgot to tell you the name. It's the cosmic grapes, because the star clusters kind of look like a bunch of grapes. If you take out the lensing, this is what it would look like with JWST at JWST resolution. And on the right, that is what you would get with HabWorlds resolution or GMT resolution. But now without lensing, so you can do this for a much larger number of galaxies. All right. Let's come to reionization. There's actually a couple cool things we could do with HabWorlds on reionization. But first, we need to understand what the process looks like. So understanding how reionization evolves basically means we need to measure the number of ionizing photons coming from galaxies. That's a key measure we can make. We can measure that as a function of position, as a function of cosmic time, and learn about the history of reionization. So to compute that ionizing photon output, we need to measure 3 quantities. The first one is the non-ionizing UV luminosity density. That's what we can actually observe. If you've ever heard a high redshift astronomer talk about the UV luminosity function, that's what we're talking about. I'm showing one here on the right. The luminosity function is just a fancy word for a histogram of galaxy UV luminosities. You measure that, you integrate it up. That tells you how much light is coming from galaxies. You need to understand a lot about the faint end, though. You can see that this thing is quite steep as you go to fainter luminosities, and I'll talk more about that in a second. That tells you how many non-ionizing photons you have. Then you need to convert that to the number of ionizing photons by learning about the stellar populations. We do that using a term, C-ion, which is the Lyman continuum photon production efficiency. Okay? When you combine those numbers, now you know how many ionizing photons are being produced. Ionizing photons don't play well with gas. They get absorbed, they ionize them, that's what they do. Galaxies, it turns out, have a lot of gas. And so all of these photons don't escape the galaxy to be available to ionize the intergalactic medium. For that, we need to know what the escape fraction of those ionizing photons are. And then when you multiply all three of these numbers together, now we get the number we want, the ionizing emissivity from galaxies. HWO is going to be able to make significant gains for number 1 and number 3 here. We'll talk about it in the next 2 slides. Number 2, we're learning a lot about with JWST spectroscopy. All right, so let's talk about number 1, the UV luminosity density. Okay? As I mentioned, the faint end of the UV luminosity function is quite steep. And so small changes in the faint end slope make for big differences in the integral of this quantity, the non-ionizing UV luminosity density. This is just one luminosity function at redshift 6 shown. So if we integrate this to the limit of the Hubble ultra deep field, something like minus 17.5 at a redshift of 6, and you assume that this function goes all the way at its steep faint end slope to minus 12, you actually only get about 1/3 of the ionizing photons. So we can integrate the luminosity function and say we're measuring this quantity, but we're mostly extrapolating. We're only seeing 1/3 of the light. Using the online HWO exposure time calculator, I said I want to do a 100-hour exposure. It told me we're going to get something like 3 to 4 magnitudes deeper with HWO. We would then be able to see at least half of that missing light, if not more. So we would turn an extrapolation into much more of a direct measurement. You might say, well, sure, but the faint end slope is probably steep, so what are you really gaining? Well, we actually think that the luminosity function is turning over at some point. You're not going to form galaxies down to sort of infinitely small scales. Obviously, a single star is a basic unit. You're not going to go below. But we do think that star formation in low-mass halos becomes less efficient for a variety of reasons. And so with HWO, you could actually start to probe for this turnover, not just learn about the UV luminosity density, but also learn about star formation in faint galaxies. And even if the aperture was the same size, this is still better than you're going to achieve with JWST. Is at this critical epoch of redshift 6, when reionization is ending, you need deep optical imaging to be able to select high redshift galaxies to see below their Lyman alpha breaks, and you cannot do that with JWST. I think the more transformative science case, however, is going to be the ionizing photon escape fraction. We heard about this in a few talks yesterday, including from Cody. There's a few posters on this as well. If we want to measure the ionizing photon escape fraction, we need to directly observe below the Lyman continuum limit. That's well into the UV. And even at high redshifts, it's still fairly blue. You also need to do this at redshift less than 4, because at higher redshifts, the IGM is optically thick. You'll never see any escaping ionizing photons. So we know this, and many, many people have been doing heroic efforts over the past decades now, but we still don't have a good answer. So just to give you a few sort of hand-picked pieces of evidence, if you do a large imaging survey, almost always you see nothing. You don't see any escaping Lyman continuum photons. When you stack the positions of the galaxies, you usually still see nothing. That's what's shown on the left here. This is a stack of many galaxies. They put an upper limit on the average escape fraction of a population of galaxies at redshift 3 of 2%. But every now and then, you might get lucky, and you might see a high escape fraction. This is an example of a spectroscopically detected spectroscopic galaxy with a Lyman continuum escape fraction of about 10%. And so if you take sort of the body of literature, say before 2015 or so, it would be consistent with the generic statement where most galaxies have very low escape fractions, with the oddball galaxy with a high escape fraction. And if you combine that with our knowledge of the UV luminosity function, you would come to the conclusion there are not enough ionizing photons for reionization. Okay? Maybe we were just looking in the wrong place. So the low redshift Lyman continuum survey, led by Ann Jascott, handpicked a number of galaxies that they thought might have high escape fractions. And lo and behold, they did find a higher fraction of galaxies with high ionizing photon escape fractions. Okay, and John Chisholm found that the escape fraction had a nice correlation with the UV spectral slope. Bluer galaxies had higher ionizing photon escape fractions. That kind of makes sense. Bluer galaxies probably have less dust. Maybe they're more primitive. Maybe the ionizing properties of the stars are harder, so the amount of neutral gas is less. So fine. If you take that relation and apply it to the UV luminosity function, now, as pointed out by Julian Munoz, you have too many ionizing photons for ionization, which is a new problem to have. But I don't think we're done yet, because JWST has now come on the scene. And in a recent paper by Casey Papovich, he modeled the nebular spectra of high Z galaxies and found that they were actually inconsistent with the Hubble LZ-LCS relation. And now we're back to not enough ionizing photons. So we basically can't agree. And the reason why we can't agree is we don't have the sample size we need to do this work properly. And this is really where HWO can come in. Clearly, we need more sensitive observations over a larger, unbiased sample. And a few ways in which HWO provided a transformative leap in this field, and hence our understanding of reionization, is that ultrasensitive UV optical spectroscopy will allow spectroscopic characterization, or you could use imaging if you like, of the ionizing continuum over all of redshift 0 to 4. A multi-object spectrograph will allow the construction of large samples. And a large sample is critical because I use this word unbiased. LZ-LCS was great, but it was not unbiased. We need large unbiased samples so we can marginalize over various properties of the galaxies, the environments of galaxies, and viewing angle is a really important one. So this is an image from a simulation of the same galaxy viewed at 6 different angles. Okay? This is actually escaping Lyman alpha emission, but Lyman continuum emission should look somewhat similar. And you can see along some sight lines, there's lots of escaping emission. And along other sight lines, there's almost none. And so we need to marginalize over this by doing large samples. So a MOS would be very useful. However, as is very popular to mention this conference, a UV IFU would also be incredibly powerful for reasons like ones highlighted in this figure. You could actually try to pick apart where in galaxies is the ionizing continuum coming out and what are the physical processes in these galaxies that are stimulating that escape. Okay. In the last few minutes, we'll talk about supermassive black holes. They've come up a few times. What I think is exciting is I was a little nervous that myself and Yuichi Harakani were talking here because we both work on kind of the same stuff, and I was worried we want to talk about the same things. And we compared notes, and it turns out we both almost came up with completely different ideas about why we were excited with HWO, but we both agreed, and with Vivian, that small black holes are going to be really cool. So I already showed you this example of a broadline region that we inferred at a redshift of 5, telling us that there's a black hole in this galaxy. In fact, we've seen black holes all the way out to, this is one example from Rebecca Larson's work at redshift 8.7, and then Anthony Taylor has a new sample of 60 black holes discovered in JWST data at redshift 3 to 9, and even more recently, redshift 3 to 7, more recently he's found one at redshift 9 as well. We're doing all of this from kinematics, looking for broad end emission lines consistent with the broadline region around a supermassive black hole. So why is this interesting? I have to tell myself this because I was not a black hole person. I still don't consider myself a black hole person, but it actually is interesting because we don't know how supermassive black holes are formed. Okay, our basic idea, the most vanilla way of forming a supermassive black hole is you take a big massive star, you let it explode as a supernova, you get a small stellar mass seed, maybe 5, maybe 10 solar masses. Maybe it's a POP3 star that was really massive. Maybe you have a 100 solar mass seed. And then you let it grow. You let it accrete gas. We think that they are limited in the rate that they can accrete through what we call the Eddington rate. It's a feedback limited accretion. And so this is a plot of black hole mass versus time. All the funny symbols are JWST black holes. The blue symbols are Sloan quasars. And the blue swath is sort of the vanilla scenario. You form with a small seed and you grow slowly. And that can create some of the Sloan quasars, but not the more massive ones, and none of the JWST black holes. So we've invented some new ways of doing this. You can start with an exotic heavy seeding scenario where the universe makes massive 10 to the 3, 10 to the 4, 10 to the 5 solar mass black holes through a variety of mechanisms, or you can grow them at a super Eddington rate. And that's illustrated by the red swath, and now you can match these observations. But so from this, we think that early black hole seeding and growth is likely pretty exotic, but we're missing something, which are the lower mass, intermediate mass black holes. I know I'm out of time, so I'll go through this quickly. JWST is limited by the spectral resolution and somewhat by its sensitivity. This red dashed line here is a rough approximation of the black hole mass limit for JWST. Something like a few times 10 to the 6. You could get around it with lensing a bit, but you can't add spectral resolution in that way. With HWO, in particular with an R of 10,000 spectrograph, you would be sensitive to 10 to the 4 solar mass black holes, showing by that orange line here, probably at lower redshift based on wavelength, depending on what you want to do. And as came up in Yuichi's talk, you do need to worry about other things that cause broad emission lines. You need to worry about outflows, you need to worry about just the dynamics of the galaxy. But if you can observe a permitted line and a forbidden line together, such as H beta plus O3, I think you could get around that. So this is kind of showing this region here, the region of parameter space that is totally unexplored that we would be able to do here. And this would be dramatically enabled by the reverberation mapping work at low redshift that Vivian talked about, because right now the relations we would use to estimate the black holes are not very well constrained at these low black hole masses. So I just want to put up my instrument wish list. High resolution imager is going to do the first science case we talked about, clustered star formation. A moderate resolution multi-object spectrograph. You could do large samples of ionizing photon escape, and with an optical IFU, you could start to get into the physics of those objects. And I just want to say 2 things before Sarah kicks me off. Number 1, these are all unique to HWO and cannot be solved with JWST. And number two, when I sit back and I think about JWST versus HWO, JWST was built to do my field. It was built to do first light in the universe, early galaxy science, right? But it's been doing amazing things for exoplanets, which weren't even envisioned when the telescope first started being designed. Now, HWO, rightfully so, is being designed to find and characterize new Earths, and that's great. But for once, I think the galaxy people are ready, are excited about the telescope and happy to go along for the ride. And I think we'll be able to do amazing science as well. Thank you.
All right, questions for Steve? See at least one.
Hi, I'm Thais Stork-Bergman from Brazil, South Brazil. I wonder, you presented this model of the little red dot. I see star formation, in the UV.
Mm-hmm.
Where are the forming stars in your drawing there?
Yeah, in our artist rendering, it's the little blue haze around it. So little red dots do have very faint blue emission.
Okay.
It's contentious isn't the right word. It's unsettled where it comes from. I tend to think it's probably from residual star formation.
Okay.
Another science case for HWO would be ultra-deep UV spectroscopy of the UV. We're trying to do it with JWST. It's hard because we're trying to look for these very faint UV emission lines to tell if it's star formation or AGN dominated.
Okay, thank you. Mm-hmm.
Another question? They're just the most important galaxies in the universe, you guys. Surely you have one question about them.
Hi there, Dan Dickin from the ATC in Scotland, Edinburgh. Just a naive question, I guess kind of naive, but I worked on JWST. The whole mantra was we wanted to go into the infrared to see to the edge of the universe, and for AGN and stuff, you can see through the dust. So now we're going to the UV. So how do we explain that to the world's population that we really wanted something with infrared and now we want something for UV? So is it really just the resolution and the sensitivity that we're going for now?
Can't we have both? I mean, I think,
yeah, no, absolutely.
We all want all the wavelengths. I think that was the challenge here is trying to think about JWST is so amazing and so transformative, but what can it not do? And so this was just a sampling of some science cases it cannot do, and that's really thinking about where do we need to go in many of these cases below 1 micron, where JWST is not sensitive or cannot even reach.
Any other questions?
It's lunchtime.
Not yet. Shh. I will also just take the chair's prerogative and say, I think as we think about multi-wavelength coverage, it's worth thinking about the Great Observatories concept and how valuable it is to have these multi-wavelength observatories that are overlapping, that at least overlap some in time and give us the ability to do this all things for all people approach. So there's several write-ups about the Great Observatories that I think is useful, especially when thinking about how we pitch things to the public, when they're like, surely you don't need another telescope in space. And we're like, maybe 2. How about more?
Can I say something that will get me yelled at?
Oh,
Probably,
yeah, I love that. Go
which
ahead.
is that it is amazing what we've learned about the early universe with JWST, and it makes you want to build an even larger infrared to mid-infrared telescope. That's not what this meeting's about, so I didn't talk about that. But I do think we don't need to necessarily tell the public why we don't want to do that. We would want to do that if that were to be an option. But there's also amazing work that you could do with this UV optical telescope as well.
Vivian, and then we'll wrap up.
Vivian Yu, Caltech, IPAC. Thank you, Steve. That was I think that as a local person, we can maybe start working together on these supermassive black holes. I really like the way you framed it. My question is, a little bit piggybacking on the last one. You've been focusing on the UV side. If we're going to talk about the infrared cutoff for HWO, do you have thoughts on what if in your science cases might constrain that? And is it merely, even in the overlap with JWST, is it merely just the larger mirror size, or if there are any other, things that you've thought about the infrared part of?
Yeah, I think definitely at the overlapping wavelengths of JWST, the bigger mirror can help. But I think really the higher spectral resolution is going to be the biggest game changer. I was thinking mostly about rest frame optical emission lines. But the higher redshift you go, the more interesting it is because the closer you are to the seeding epoch. You talked about carbon-4. I think that would be exciting. Going really sensitive in the UV, you could pair carbon-4 with the forbidden oxygen-3, and then you could do the same type of analysis out to higher redshift.
That'd be really cool. Thanks.
All right, we have two things, so don't escape while you're clapping. First, let's give a round of applause to Steve, as well as the whole session, our panelists, our other speakers, and then just a quick announcement from Janice, and then we all get to have lunch.
Good afternoon from the flight deck. We're about halfway through our flight, so it's 2/3 away from our flight, and we have smooth skies. Have about 18 hours before we land. So I wanted to talk to you about our flight log, but I think we don't have the slides for that. So I'll just say a few words now, and then we'll talk about it tomorrow, because I think the crowd has thinned out. So what do I mean about the flight log? What do you think I mean? The conference proceedings, yes. So I just wanted to thank the people who have volunteered so far to be the editors of this monstrous conference proceedings. And I wanted to introduce Jonathan Barnes, if he's in the audience. Is he here? Say hi to everybody. Thank you for taking on this very heroic task. He has a table outside, so if you have any questions at all about submitting conference proceedings, please ask him. There is a LaTeX template on the HWO conference website. So if you're looking for a LaTeX template, it's there. But right now, it is not generic. It's for the science cases. And then maybe I'll talk about the other things when we have the slides. The other thing is that we're going to switch modes right now. We have 3 parallel sessions, right? And if you take a look at your programs, it'll show you on the other tabs where those parallel sessions are. So we're going to be running an exoplanet parallel session here, and there's going to be one on 8 and one on 9. Okay? And as always, 2 o'clock. So enjoy your lunch.